the following. When they're asking, okay, you're going to take, how much will $1,000 purchase in 4 years? What that means, what that really means, is $1,000 today, right? $1,000 today will buy less goods and services in 4 years. Well, how much less? I mean, we all know it's going to go down. How much less? They effectively said, with their little formula, you just take away 3.5% every year. That's not right. That's not right. That's not what inflation does. What it means is a lower amount of goods and services today, call that P, call it Joe, whatever you want to call it, a lower amount of goods and services today will go up by 3.5% in price. That's what inflation means. And then again, and then again, and then again, 4 years, 3.5%, and then it'll become $1,000. That's what it means. Does that make sense? Something of lower value today grows to become $1,000 in 4 years. That's what it means when you ask somebody, what will $1,000 today purchase in 4 years? You mean what lower goods and services today will grow to become $1,000 in 4 years? They got that reversed. So in other words, we're saying what amount today, what amount of goods and services today, it's like an economics thing, isn't it? We're doing economics class today. You like economics? I only got to take one economics. I loved economics. That was very interesting. Anyway, but I like math, so obviously that probably fit. So lower amount of goods and services today will grow by how much? Well, it's our little formula. You just use our little formula. To become what larger amount, that's where the 1,000 goes. You say $1,000, well, what lower amount, P, of goods and services will grow at, what's the interest rate? 0.035. We're talking 4 years. No. Compounding is just once a year, huh? Compounding is once a year for 4 years. There's what you do. You don't do that. They put a minus in there because they were effectively, what they were thinking backwards. They were thinking, you just take 1,000 and you lower it by 3.5% per year. That's not the same thing. I don't know if you've ever thought about percentages carefully before. Do you realize that if I take $1,000 and I lower it by 10%, let's say it goes down by 10%, it becomes 900, right? But if I take 900 and raise it by 10%, it doesn't go back to 1,000. What does it go to? 990. You see, that's not the same thing. It's not because when you lower the 10%, you're lowering on a bigger amount. And when you raise the 10% from the 900, you're raising based on a smaller starting amount. So the jump isn't as much, right? So that matters. That's not the same thing to take the 3.5% inflation and say, oh, just take the 1,000 like they did and just lower it 3.5%. No. That's not what inflation does. Inflation takes a lower amount of goods and services and raises it by 3.5. So basically, that's really the formula. I'm not going to put it on the test because it's all convoluted now. But that's the real formula. So let me solve this real quick. So 1,000p 1.035 to the fourth, right? So then just divide by 1.035 to the fourth power, 1.035. So if somebody have a calculator, what's 1,000 divided by 1.035 to the fourth? That'll be the lower amount, like 800, 900. 868.08. So 868.08. Oops, it's off the screen there. 868.08. Here, I'll move it over. 868.08. 868.08. That's really the lower amount of goods and services that will grow to become $1,000 in 4 years, right? They said the answer was 867.18, right? And that's where I thought, well, maybe I'm crazy. I mean, it just doesn't seem right to me how they're thinking. So then I went over to the something. Right, so they skip those last three questions, right? Everybody good with that? So skip, you probably already did. I think we did. It's over, Mr. Aaron. It's over. 24, 25, and 26 on 5.7. Just skip them. They mishandled that. Even authors of books make mistakes. Let's go here. All right. So population of a colony of mosquitoes. Mosquitoes? That's how you spell mosquitoes, huh? Mosquitoes obeys the law of uninhibited growth. There are 1,000 mosquitoes initially, and there are 1,200 after 1 day. Wow. What is the size? The words are off the screen a little bit. What is the size of the colony after 4 days? How long is it until there are 70,000 mosquitoes? Okay, so There we go. All right, so what formula are we going to use on all these exponential growth and decay problems? Wait, why does my screen look so weird? Oh, I don't know. I'm having some kind of technology problem. Anyway, there it is. The PERT, right? Everybody with me? They use a different formula when they set it up on Math Excel. It's effective. I think they call it A equals A0 e to the KT. That's the same thing. You can use either one you want. I thought I would just keep using the same one because you guys are used to it now, and it'd be easier for you. But you know it's all the same. Don't be thrown off if you click on the help button and you see this. It's the same thing, right? These letters could be any letter, right? It's just something in the front, a power up here, call it K, call it R, whatever, and the T variable up there. I'm just going to keep using the PERT because we're used to it. All these are continuous. Whenever you have like organic things, living things, growing or decaying, it's a continuous compounding is effectively what it is. You use the E. It's PERT. All right, so here we go. Population, what is it? Now I wrote over the numbers there. So there's 1,000 mosquitoes initially. Okay, where does that 1,000 go then? Yeah, good job. That's like the principal investment, huh? That's like the money you put in the bank first. In this case, we're putting mosquitoes in the bank. All right, and there's 1,200 after 1 day. 1,200 after 1 day. So what are we going to do about that?
T is 1, right?
Yeah, right. We're going to put in T is 1 day and amount is 1,200. In other words, there's 1,200 after 1 day. We can use that to find R, and then we're going to restart and use the PERT formula a second time to finish the question. All right, did you catch that? That's the way all these are going to work from now on. They're going to be in 2 phases. In fact, let me get to a fresh, I don't know, my computer, do that. Let me see. Okay, good. Looks normal now. All right, so let me try again. So same question. Here we go. So phase 1, so it's always going to be 2 phases. Phase 1 is find your R, or they'll call it K. You know, find that little constant up there. And then phase 2 will always be finish the problem. So I think that'll help you if I kind of break them into 2 phases for you. So phase 1 is find R. Phase 2 is finish it up. So phase 1, I'm going to use the PERT. But again, you could use their A0 e to the KT if you want. Okay, so here we go. So there's 1,000 mosquitoes initially. That's the P. And again, after 1 day, the amount is 1,200. So everybody good with that? Oops, kind of getting scribbly over there. So we good to there? So the amount is 1,200. 1,000 is the original. After 1 day. So when T is 1 day, the amount becomes 1,200. Use that to solve for R. That's phase 1. That's what phase 1 is all about, is getting your hands on R. And then as soon as we have R, we'll start again with the PERT formula, then knowing R. All right, so how do we solve for R here? Get rid of that 1,000 first off, right? Drop the 1,000. That's 1.2 is e to the R times 1, just e to the R, right? And now what do? R is where? In the power zone. So what does that mean we do? Natural log. We know. We dethrone it, right? Natural log on both sides. The R comes down. Natural log 1.2 is R ln E. And that's just 1. So R is natural log of 1.2. I'm just going to leave it like that rather than get some long, ugly decimal, you know? Just going to leave it natural log of 1.2. That's R. We good so far? So that's the end of phase 1. Now take that back up here to phase 2, and we'll use the PERT. Same formula again. Start with the PERT again. But this time you know what R is. It's ln of 1.2. So you go, oh, okay. So it's ln of 1.2 times the T. You don't have to put parentheses around that ln 1.2. I did just to make sure we didn't think the T was part of the plug-in to the natural log function. I'm just trying to be clear about where that T is. It's not in the toaster, right? On that. Okay, we good to that point? Let me see. I could do a trick here that would make things easier, but I wonder if it might be confusing. Oh, and the P's 1,000, isn't it? Let's just put that P back in. That P's still 1,000. That doesn't change. That's the initial amount of mosquitoes, the initial investment. All right, now what's their final question? 4 days. What's the size of the colony after 4 days? So just plug in T is 4. Yeah, I'll skip the trick. This is good enough. Well, the trick is helpful. These cancel. The E and the natural log, remember how those are opposites? You can cancel those, but careful when you do. The T's still in the power zone. The 1.2 drops down, but the T's still the power. Do you see what I mean? Is that confusing? See how the whole ln 1.2 times T is up in the power zone? When the E and the ln cancel, the 1.2 drops down. The T is still in the power zone like that. Does that make sense on that? Okay, so anyway, plug in your T. Your T is 4, right? T is 4. 4 days. Hit the buttons. 1,000 times 1.2 to the 4th. Anybody got a number for us? It says do not round. 2,000. What does it do? Oh, it says don't round until the final, then round to the nearest whole number. Okay, I can. Is it round 74? Okay, thank you. Thank you, Michael. 2074 then. It's a lot of little mosquitoes after 4 days. Is that good to there? Then we're going to do the second part, which is how long until 70,000. Yeah, by the way, yeah, you know what? Their whole thing about not rounding in the middle, what they mean by that is important. You got to follow their instructions on that. That means they don't want you to make this some big long decimal, because you're going to have to cut it at some point, because it'll be a decimal that goes forever. So you would have to round. So they want you to leave it ln 1.2 like we did. They want you to do it like we did. And in fact, I think they'll probably, I don't know if they show this trick or not, they probably do. So this would be a good habit. It'll just make things clean and easy for you. We good to there? So I'm about to go to the new page, and then I'm going to do the 70,000 mosquitoes. All right, so remember this formula. We're going to keep using this exact, that's our formula. Well, actually, with a T, because T's not always 4, right? There's really our formula. For any number, remember that was T, and we put in a 4 here. Right? Put in 4. So, okay. So let's go to the new page and answer the second part. So it's A equals 1,000. What was it? 1.2 to the T. That was the formula we finally came up with. We plugged in 4 to get the answer to the first part. Now they're going to say, how long until there's 70,000 mosquitoes? How long? What do they want from me? How long? They want time. They want time. So what am I going to do with that 70,000? That's the amount. Yeah, that's the amount of mosquitoes later. And you want to solve for time. So, what you going to do? Divide by that 1,000, yeah. Yep, we've done it several times now, right? You can do it in your sleep. Right, T's in the power zone. Natural log brings the T down, so ln 70 is T ln 1.2. And last step, divide by ln 1.2, ln 1.2. So T equals, somebody got a number on there? 23.3. Round to the nearest whole number, so we'll just say 23. Is that days? Yeah. It's days, huh? In 23 days, we got 70,000 mosquitoes. That's how they calculate some of these biology formulas. Is that good? Questions on that? All right. But we probably won't. All right. The population of a southern city follows the exponential law. If the population doubled in size follows the exponential law. When they say that, follows the exponential law, they mean, hey, you can use the PERT formula. That's what they mean. They mean it's growing like continuous compounding, like money does with continuous compounding. Right? That's the formula for exponential growth, basically. That's what that is. And again, you could say, the book will say A equals A0 e to the kt, same thing. Doesn't matter. As long as you've got an E and the T's in the power zone, it's the same thing. So if the population doubled in size in 14 months, and the current population is 80,000, what will be? Is that what it says? Yeah. What will the population be 3 years from now? Okay. Want to give it a try? Remember again, it's 2 phases. I think that'll help you. Just think in 2, because people get confused when they try to do the whole thing at once. Just think, phase 1, what's the goal of phase 1? Almost always, the goal of phase 1 is find your R, that little constant that's up there. So go ahead and take some information they've given you, take the PERT formula, and plug in what you can, really everything but R. That way you can solve R. Save this for later. That'll be, the 3 years will just be for part 2. That'll be for the conclusion. But use the double in size and 14 months, plug those in, and find R. See if you can do that. I'll give you a second. Double in size in 14 months. Double in size. What does that mean? What is A? Oh, yeah, actually, I guess, yeah, the current population is 80,000. Yeah, thank you. So the current population is 80,000. Double would be 160,000, huh? So 160,000 equals 80,000 e to the r, and that's in what, 14 months? Does that make sense? Yeah.
You don't have to plug the number. You
right.
Just use 2 because we wanted to use 2.
Totally. Yeah, if you wanted to just make A be like 2p, and you can save the 80, we'll need the 80,000 in part 2. But yeah, that's another way. You can then just divide the p off both sides. That's fine, because that's what's going to happen. See, we're going to get the same thing on our first step. We're going to divide by 80,000, and what's that right side going to be? There's our 2, Yeah, so either way, yeah, totally that'll work either way. You can put in the actual numbers or just do the 2. Now, don't make this mistake, though. Here's the mistake I've seen over the years that students make. So that's why I hesitate to show you the 2 thing. Because people will see double, and they'll go, I remember that's just 2, but they'll leave the p over here. And then they'll get all stuck. They're like, oh, shoot, what's the p? Then they'll put in the 80,000. And then they're just all messed up, right? So careful on that, right? It's 2p, really. It's 2p, and the p's drop out. Right? Don't forget, the p's drop out if you're going to do it that way, which is fine. All right, so what do we do now? Yeah, because the letter's up there in the power zone. So ln, the power drops down. What do we got? ln2 is whoops, I forgot to put the power in the front there. It's 14r ln e, and that's just 1. So then just divide by 14. R is ln2 over 14. I'm just going to leave it that way. Right? I don't want a messy decimal, and I can't round halfway through. You never want to round in the middle of a problem, because rounding at the end is fine, but not in the middle. It'll throw things off. Okay, phase 2 now. Phase 2, we're going to use the PERT formula yet again. This time we know the R. See how this always works? Phase 1, we get our hands on R. Phase 2, we start again. Now we put in the R. Now we put in the P. P's 80,000. The R is ln2 over 14t. We good to there? I want to do some trickery with that little power thing. You with me? Everybody caught up? We on the same page? I don't want you to miss this. Basically, how do I say it? This maneuver confuses people sometimes. It's a little tricky. Basically, these guys are going to cancel, right? E and the ln. But the confusion is what happens with the 14 and the... See, the 14 is not in a natural log. The 2 is, right? So remember, the E and the natural log cancel. What was in the toaster comes out. But he drops down to the base. And the T and the 14 are going to remain in the power. It's kind of confusing, huh? Do you see that? So in other words, one nice thing to do is just forget about everything else for a minute and just look right here. Forget about the E, forget about everything, just look right here. It's a fraction, right? One thing over another times something. So that's really T over 1, right? I can make that T over 1. It's just a fraction, right? And so what? So then what's the bottom? 14 times 1? 14. So really I could, and it'll make it easier, move this 14 over here, right? That's the same thing. It was under the first one, it's under the second. Oh, can you see it's off the screen there? Huh? Just move it over a little bit, okay? And that'll make life easier because then when you cancel these guys, it makes sense. You don't get confused. The 2 just drops down to the base, and the T over 14 is still up here in the power. Does that make sense what happened? You don't have to do that. I'm just trying to make it make sense here. The E and the natural log cancel, and the 2 drops down. It drops down. Like that. To the base. But don't be confused. The T and the 14 stay in the power zone. So there's our formula. We can do anything they want now. Anything they want to ask us, we can solve now that we've got our hands on that formula. What's their question? 3 years from now. Good job. Yeah. I wish they wouldn't play these games of changing the units. There's enough to worry about. But they are. Remember, our formula was in terms of months, right? 14 months. So that all the work that we've done in setting this up, this 14 is months. So that means we're in months now. So when they ask me 3 years, I got to change that to months because my formula is set up for using months, right? We based it on months. So, okay, so 3 years times 12, 36 months. 36 months. So that means take that 36 and plug in. I'm just running out of room in a hurry here. So it's going to equal, plug in 36, 80,000 times 2 to the 36 over 14 power. Does that make sense? Time is 36 months, 3 years. And then just hit the buttons on the calculator. What is that? It's almost 3, 2.5, so 4, I don't know. It's like 3 to 400,000, maybe? Is it 3 to 400,000? Somebody got an answer?
475,518.
Yeah, that sounds about right. It says round to the nearest whole number. So that was the correct rounding? 518? Anybody else getting that? 475, 518? That's how many people in 3 years. Is that okay? You guys able to get that in your calculators? It's a good thing to have a calculator with you. Right, 2 to the power, 36 over 14, times 80,000. Questions? We okay? I don't see a lot of happiness. I don't see like a yes, Mr. And that's making total sense. Thea, can I help with things that make sense? So let me run over the whole thing for everybody again. So 2 phases, PERT formula, right? We plug in the 14 months, 80,000, 160,000, which ends up being the 2. Solve for R. Our R ends up being ln 2 over 14. It's a little tricky here when you put that in. The E and the ln cancel. 2 drops down. Remember, the 2 comes down. 2 over 14 power, plug in 36 months. And hit the buttons. Okay. Half-life. All right, the half-life of radium is 1690 years. What does half-life mean again? How long till half's gone? Or half remains, however you want to say that. Half cup full, half empty. Right? How long till half remains? Right? 1,690 years. Right? So if you have a chunk of this stuff, whatever it is, radium, if you have a chunk of this radium sitting around in your office, your lab, after 1,690 years, half of it will be dissipated, just float away, right? So in other words, if you start with 100, if you start, say, with 100 grams of it, then 1690 years later, you'll have 50 grams. And then if you wait another 1690 years, it's hard to do that, you'll have 25 grams. And then you wait another 1690 years, you'll have 12.5 grams. Does that make sense? So it's not the same amount going away, it's the same percentage, half, going away every 1690 years. That's what half-life means, how long till half is gone. Okay, so with that in mind, that tells us something about, it's the same kind of deal as the last one. You know, we have phase 1, find R. Phase 2, finish up. So same formula. The old PERT formula, I'll write it up here. The old PERT formula. Whoops. All right, so give that a try. Let me let you do that. So phase 1, you're supposed to get R. Find R. So what does it mean? What's A going to be? What's the amount going to be? The amount's going to be, oh, is there 40 now? Yeah, 40 now, so we can just make it 20. Yeah, or half P, or 0.5P. Either way you prefer to do it. You could make the A 0.5, whoops, you can make the A 0.5P like that, or half P, right? And then drop the P's out. You're just going to have a 0.5 over there. That's fine. Or you can put in the actual numbers, which is what? They're telling me 40. P is 40 because there's 40 grams now, and half of that means 20 grams later. Oh, and later, how long later? Time is 1690. Right? When time is 1690, there'll only be 20 left. Or, you know, and then divide by the 40. You see we're going to get that 0.5 anyway. Does that make sense? So you either want to go directly to the 0.5 or just put in the actual numbers and divide, you'll get 0.5. Either way. We got ourselves a 0.5, half. All right? You know the next trick, right? Natural log of both sides. Natural log, and the power drops down. Ln of 0.5 equals R 1690 ln E, which is just 1. So divide by 1690. 1690. R, got our hands on R now. R is ln of 0.5 over 1690. Now we're going to do phase 2, right? We'll finish up the problem. But let's pause for a second, and let me give you a shortcut. If you get a, anytime they give you a half-life question, right? Remember, this is, and there's going to be a few of these. There's going to be like, I don't know, well, maybe only two or three, but they're common. If you get a half-life question, they go blah, 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 the half-life. If you want to save time, phase 1 will always end up being the natural log of 0.5, R will always be the natural log of 0.5 over the number of the time, basically. Do you see what I'm saying? It'll always end up being the natural log of 0.5 over time. So if you want to just skip phase 1, when they tell you half-life 1690, you just go, oh, R is ln of 0.5 half over 1690, which we end up finding anyway. So if you want to save some time, you can do that. Does that make sense? I remember showing my daughters took pre-calculus last year. And I showed, they were taking Mr. Jameson here. And I showed them this little, they were doing half-life problems. I'm like, here girls, here's a trick. When you get a half-life on the test, just do this, you know. And I remember my daughter's like, yeah, but Mr. Jameson can be tricky. If you ever taken Mr. Jameson, he's tricky. He loves math. I love talking with Mr. Jameson. What if he gives us one that's tricky where we get, I don't think he will, girls. I don't think he will. So I showed them the trick, you know, they took the test. Sure enough, he put a tricky one on there where you couldn't use this. They were all mad at me because I gave them a shortcut trying to help them. Anyway, so you might want to know the long way and the short way. So that's the quick short way. Boom, right there. There's the short way. So now let's do phase 2. So phase 2, going to use the PERT formula again. And now we know R. So, oh, and what's the P? 40 grams. The P is 40 grams. And the R is ln 0.5 over 1690 to the T. There we go. We good to there? Everybody good? Now remember what happens? The E and the ln cancel. Am I going too quick? This is where I confuse people. So I want to go slow here. Is everybody dialed in with me? Everybody see what's happening? This is where I often get a lot of questions. See how the E and the ln are going to cancel. What is going to become the base? What's going to drop down and be the base? 0.5. The 0.5. The thing that was in the toaster. Right? When the E and the ln cancel, out pops the thing that was in the toaster. Right? Because we're removing. And the 1690 is going to slide over here, really. Because it never was in the toaster. Right? It was just a power piece. It was never plugged into the ln. It's not being freed up from anything. But the 0.5 is. Right? Everybody see that? So 0.5 to the T over 1690. Yeah. I mean, really, you could even jump to there. Every half-life problem will end up being A equals P, 0.5, that's the half, to the T over the half-life number. Really, it will. All right. So now what? Oh, 380 years. Now plug in the 380. So 380 over 1690. Hit the buttons and you get something. Somebody got it? Not much of that stuff should be left. 34? What do they want? They want, nearest 1,000. They want 3 decimal places. 227? Anybody else getting that? Is that good? 34.227 of that stuff left. Yeah, because 380 years, that wasn't even the half-life, so there's going to be more than half still. More than 20 is going to be left. Because it takes 1690 years to get down to 20. That's only 380 years. Is that good? Are we good on that? Questions I can answer? That's just the PERT formula again and again. And for half-life, you could just jump all the way down to here, really, if you want. I mean, that would be like a 2-stepper. Half-life will always be 0.5 to the T over the half-life. That's what it'll be. All right. A bit of a wrinkle in most of these. They're a little tricky. Okay. Half-life of carbon-14, 5,600 years. Piece of charcoal. Yeah, so this is how they can carbon date. So we'll do an actual carbon dating problem here to figure out how old something is. So the deal is, do you know the chemical deal? Carbon-14, what is it? Which one is it that stays? And one of them, I'm not a chemist. I just took the bare minimum chemistry. One of the carbons decays and the other stays. That's how it's like a time clock, therefore. I guess it's carbon-14 that begins to decay and some other type of carbon just stays. So when they find a piece of something that was once living like a tree or an animal or whatever, they can measure the 2 kinds of carbon, and the one kind of carbon that stays, they know, oh, this must have been the amount originally, and then they can check how much carbon-14 is left, and they know how much that's reduced. That's how that's working. So, all right, so they're telling us, look at carbon-14, and its decay rate, its half-life is 5,600 years. So can we jump right to the, so half-life, was it 5,600 years? So remember what we can do. We can just go A is 0.5, that's the half, to the T over, I'll just stick it right here, half. That's what you can do. Yeah, here, let me just give you that formula. That's the little shortcut formula. All you have to do is 0.5 to the T over the half-life. That's the little formula I gave my daughters last year. And then Mr. Jameson gave them a really tricky question instead. All right, so you ready? 0.5 to the T over, what is the half-life? 5,600. So there's our formula. I totally skipped phase 1 by just using that. Just jump right to here. And so then all we got to do is, no, they are being a little tricky. Okay, they're saying when, their question is, there's the question word, who, what, when, where, why, how. When did the tree die? When? What do they want from me? When? They want time. When? They're asking for time. They're telling me it shows that 74% of the carbon-14 is left. 74% of the carbon-14 is left. Oh, there should be a P here. I'm sorry. Yeah, sorry. Let me try that again. So there's a P in front there. A equals P. Right? Anyway, 74% is left. What do I do with that? We just do phase 2. So all we got to do is phase 2. Just finish up. 74% is left.
The P would
Kelton.
be 1, and the A would be 0.74. Yeah?
That'll work. That'll work. Or you could just say A is 0.74P. P's will cancel. Same effect. What you did will work fine too. Right? Because if 74% of, what does that mean? Times. 74% of the original is left. 74% times P is what amount is, right? So the amount is 0.74P equals P, 0.5 to the T over 5,600. Does that make sense? Then the P's just cancel, don't they? So yeah, so what Kelton was saying will work. 0.74 is 0.5 to the T over 5,600. Are we good to there? Oh, it's going off the screen a little bit. It's like the thing changes day by day. Sometimes there's more in the screen, sometimes there's less. Yeah, good. All right, so we get to there. What do we do now? We got to solve for T. Ln, yet again, T's in the power zone. So Ln, the power comes down. So Ln 0.74 is T over 5,600 Ln 0.5. We good to there? Got to solve for T. So what are you going to do? Couple of things. Divide by the Ln 0.5. Right? And I'm really out of room. And then you got to multiply by the 5,600. Can I go? I'll go to a new screen here. Ln 0.74. Go back. Everybody copy that down okay? Whoops, I think I wrote that wrong. Maybe I'll fix it. Right, everybody see what we did here? I just divided by the Ln 0.5. So T over 5,600 equals Ln 0.74 over Ln 0.5. Is that good to there? Can I go to the new screen? Anybody need me to wait? You got it? And I wrote that wrong. It's supposed to be T over 5,600. Yeah, so then what do we do to finish solving for T? Just multiply by that 5,600, right? So there it is. Hit the buttons on your calculator. Somebody got it? 2,432. Is that rounded? What do they want? They want rounded to the nearest whole number.
2,433.
Goes to 33? Okay. That many years old. That many years old by the amount of carbon-14 that's left. Good on that? Questions on that? Yeah, that was years, I think, huh? Yeah, years. Real old. We okay? So you got that first page down? Everybody good with all that? All right, we've... Okay, so it's Jeff tested the water, found the amount is 2.6. 24 hours later, it went down to 2.3. So there's the crucial facts. All that other blah, 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 blah. It was at 2.6. That's our principal investment. 24 hours later, it dropped to 2.3. All you need to know is a start, an end, and a time. And then you can do phase 1 and get your hands on R. Because basically that's how fast things are going away. That's what that R is. It has to do with the rate of decay. That's exactly what it is. The R is the rate of decay. So once you know it went from here to there in a certain amount of time, boom, that's enough. You want to think, okay, that's enough information for me to get my hands on R. So we're going to use phase 1 again. A equals PERT. I'm just going to probably set this one up. I'm going to set these last 3 up for you because that's probably the hard part. You can do all the Ln stuff, I think, at this point. So 2.6 is the P, right? That's the initial amount. These are decaying things. So they start with more, end with less, right? The amount later is 2.3, right? And that was in 24 hours. Time will be in hours then. 24 hours, 2.6 went down to 2.3, huh? Right? Then you solve for R, divide by 2.6. I would just leave, I think 2.3 divided by 2.6 is some ugly decimal. I mean, a decimal that goes on forever. I'm pretty sure. So if that's the case, I'm just going to leave it. Because I don't want to round in the middle of the problem. Right? Does the decimal go forever?
Yeah.
Some say yes, some say no. 2.3 divided by 2.6?
Not forever, but.
What's the decimal?
0.88461538.
It just goes on.
Yeah, that means forever when it's off to the edge and it, yeah. So yeah, we don't want to do that. So instead, I'm going to say, okay, I'm just going to leave it. When it's really ugly like that, just leave it. And just do the ln of both sides. ln, power drops down, so we get 24R ln E, that's just 1, is ln of 2.3 over 2.6, divide by 24. Boom, so there's R. And then we're ready for phase 2. Phase 2, PERT formula yet again. Now we know all of that mass is R. And the P, what was the P? The P is 2.6 still, right? That was the initial amount of the pool, 2.6. E to the R, ln 2.3 over 2.6 over 24 T. Look at that mess. Is that okay? Plugged in R there. And remember what happens? The E and the ln cancel, and this part, which was in the toaster, drops down to become the base, right? You with me? So 2.6, and then the 2.3 over 2.6 is the base, to the T over 24 power. Just barely off that screen, huh? We good there? Everybody see what happened? See how the E and the ln always cancel. What was in the toaster drops down to be the base. The T over 24 remains in the power zone. Is that good? And then you would just plug in the 48 hours. Just plug in 48, get your answer. Part 2 says how long till it's something? 1.0 or something? I think the second question is, you just got to make the amount be 1.0. You can do that. I'm going to skip on. Is that okay with that one? And the homework. Here we go. So carrying capacity is just the number on the top. This is a special kind of formula. Percentage is just right there. Change it to percentage. Initial population, what does initial mean? Initial means at the start. And at the start, time is 0. Whenever they say in any word problem, math, chemistry, physics, whatever, initial, you go time 0. That's what they're saying, time 0. So just take that little formula, 2001 plus 34.43, e to the 0. Just plug in 0 for t, 0 times 0.34 is 0. And that's just 1, so it's 2000 over 35.43, whatever your calculator says that is, right?